Now that we have seen the structure of a Fischer projection, we are going to now use it to determine enantiomers and diastereomers. To do that in these molecules is not too difficult since we don't have to rotate them, or we cannot rotate them. So it's just what's in front of us is what we see. So we begin by drawing our imaginary mirror in between these two. And we're trying to determine if they are mirror images of each other. If they are, then it's going to be an enantiomer, and if they are not, then we'll call it a diastereomer. So what you see is these OHs facing each other, and it continues on down. These hydrogens are facing each other, and these OHs are facing each other. The rest of the molecule is the same. Notice that on the bottom it's both CH2OH, and on the top it's CHO. Okay, and then on the other side, the OHs are away from each other, H's, everything lines up, and everything is a mirror image. So this makes these two molecules enantiomers of each other. Let's now look at another example. In this example, again, we're going to go ahead and decide whether it's enantiomers or diastereomers. And so what we're looking at here is that mirror in the middle, trying to see if these are mirror images of each other. And we'll go down again and match it up. So OH, H. Right off, we notice that it doesn't line up correctly. They're not being mirror images of each other. Again, H, OH, not a mirror image. The bottom ones are mirror images. So that is what we can see. Clearly the whole molecule is not a mirror image, and so these molecules are diastereomers of each other. And that's how we determine whether something is an enantiomer or a diastereomer in a Fischer projection drawing. Moving on to another concept of Fischer projections, instead of using the S and R configuration when we're dealing with chirality, we use the L and D for our monosaccharides. And so when the monosaccharides are drawn in a Fischer projection, we're going to look towards the penultimate carbon, and the penultimate carbon will be the last carbon at the bottom of the chain that is chiral. Okay, and so you know what a chiral carbon is because every time you see this fishbone throughout the molecule, you have a chiral carbon. We only fishbone the chiral carbons. But the ones at the bottom, because they're not fishboned, they're not chiral. Okay, so the penultimate carbon in the left molecule will be this one right here. So what we're going to do is we're going to look and see, is the OH on the right or is the OH on the left side? And in this case, the OH is on the right. And so right means that this is a D conformation. Okay, and again, it doesn't matter how long the Fischer projection or the carbon chain is for our monosaccharide, we are still going to look at that last chiral carbon. Okay, and so even though it was only 2 carbons down, for this one, 1, 2, 3, 4 carbons down, we locate the penultimate carbon because it is the last fishboned carbon. Again, we now want to assess which side the OH is on. Is it on the left or the right? And we notice it's on the left. And so if it's on the left, it is L configuration.